let's go ahead and get started. So the lectures kind of come in chunks, if maybe you've noticed. And so this is the last of the sort of enterprise systems lectures. We're talking about different hardware components. And then we're going to take a departure and sort of hopefully learn a chunk of information. And then starting in the next lecture, we're going to get into sort of, ever closer to imaging, right? The thing that we probably mostly care about. So we'll get into how pulse sequences come together, how they result in image contrast of various kinds, how we form things like echoes, and then understanding why we do imaging in the way that we do before we get to sort of some of the so-called advanced topics of my lectures. So I'll go through the normal at the beginning here, and then we'll get into talking about gradients. And so in the last lecture, in the last lecture, I'd like to give a summary of sort of where we were and sort of what we got to. So a couple lectures ago, we worked at defining the block equations in the rotating frame, right? How do we hop into the system of spins and process around with them? And the system of equations actually looks reasonably similar to the equations in the rotating frame. We just have to take into account this thing we call B effective. And then starting in the last lecture, we really got into this concept of introducing this idea of relaxation, that the bulk magnetization wants to return to some equilibrium condition, and it's driven by two things: T2 decay, so the transverse magnetization wants to decay, and T1 relaxation, the magnetization wants to grow back, the Z component of the magnetization wants to grow back until it gets back to the so-called magnitude. And so anytime we're dealing with the equation of motion, or the block equations rather, in the rotating frame, we have to define this B effective. This is the effective B field in the rotating frame. And there's always this constant term that we add onto the front, which effectively demodulates the presence of that external B0 field. And so the thing that you have to sort of think about with each of these problems is what is B rot, and this is the applied B field as expressed into the rotating frame. We don't usually think about the rotating frame because we usually think of the lab frame, because that's how we build and design a system. So most of these things are designed in the laboratory frame, so we have to go through this conversion. So with conventional MR systems, everything we're going to talk about in this class, we know how to define omega rot. It's always going to be the same thing. That's the good news. If we're just talking about free precession is when we only have the presence of the B0 field. We'll talk today about adding gradients to that field, but it's sort of these static fields, which are very distinct from, say, the radio frequency fields. And if we do that, just adding in the free precessional field here and the conventional field into defining B effective, we just get 0 B effective, so there's no background field. And now these equations become a little bit simpler. This is the equations for free precession in the rotating frame, but now we've added relaxation. And had we not gone into the rotating frame, we showed previously, you end up with a really complicated set of differential equations for which there's no general solution. So we kind of threw up our hands and said, well, if you care about it in the laboratory frame, you can tackle this with simulation. Here we actually end up with a system of equations that we could separate out, and it didn't end up looking so bad. And so when we look at just the MZ component of the magnetization, this is the expression. We're going to use this a lot in the next 3 lectures. So you will at some point memorize this, whether or not you do so actively or passively is up to you. But we'll use this expression a lot because it always tells us what's happening to the MZ magnetization during periods of free precession. Right? So free precession is we've acted on the spin system, we've forced it to do something with RF pulses, and now it's going back to some equilibrium state. And so this expression tells us that the MZ component of the magnetization is a function of time. It will have some initial state, MZ naught, that decays. Right? It's going to decay away as a function of time. Any magnetization you prepare is unstable, so that state's going to dissipate. And then there's the second term, which is the regrowth of the magnetization. The magnetization wants to get back to M non. And if you carry out these expressions at, say, time 0 or time infinity, they'll collapse to really simple things. And so we talked through a couple of examples of what happens to the magnetization after different sort of RF pulses and so forth. So what's my starting state? How do I end up with this starting state of having my initial magnetization be minus M non? Just an inversion pulse, right? So just tip all the magnetization upside down. And if my proton densities are mostly the same, then I'll have the same amount of magnetization for all compartments, right? Whether it's white matter, gray matter, or CSF. In principle, these would all be slightly separated, right? In principle, the proton density of CSF, I think, is quite high. And it's lower for white matter. And so this shows what's happening to the z component of the magnetization according to this equation here as a function of time. And everything is going back towards equilibrium. If we wait long enough, these things will get all the way back up to M0, right? Now, the tricky and somewhat unfortunate thing in MR, and this is a topic we won't get to for a little bit, is that we really look at the magnitude of these signals in MR. We're detecting the magnitude of the flux in the coil, we're detecting the voltage. And there are ways to do so-called phase-sensitive detection, where you could actually track the so-called negative magnetization, recovering through zero and going positive again. That's a topic we'll get to later. 95% of the time when you're looking at MR images, you're looking at so-called magnitude images, the magnitude of the detected magnetization. So that's okay. It just causes this kind of funny bounce behavior in the signal. And so we worked through, I won't go through all of them right now, probably. But we could understand that if we plotted those equations for white matter, gray matter, and CSF, we would trace out these different histories of the MZ magnetization. And the whole business of imaging is sampling the magnetization. Imaging is sampling the magnetization, right? We can prepare it with an inversion pulse in this case. And now our job is to say, well, do you want this picture? If so, you better generate an image very quickly. If you want an image with a different kind of contrast, this is a pretty extreme form of contrast where the white matter is really dark. If that's what you want, play an inversion pulse, wait about 500 milliseconds, and form an image as fast as you can. And that's the snapshot of the magnetization that you'll get. And so a lot of MR is about playing preparation pulses of various kinds to manipulate the bulk magnetization, and then timing the imaging experiment to capture the contrast that you want. How you time it and how you capture it is the lectures that are coming. We had another expression, so this is again what happens to the transverse magnetization when it's free precessing. At this point, things I get a little sloppy, perhaps, because I really should write this as the X prime Y prime magnetization. We're in the rotating frame. This is what's happening to the transverse magnetization in the rotating frame. The only thing you see in the rotating frame is whatever initial or prepared magnetization you have is decaying away as a function of time. In the laboratory frame, it's decaying exponentially, like these curves, but it's also still precessing, and that's kind of a headache, right? So, apology, no apology. I'm not as careful with my primes after a certain point because they just get annoying to keep track of. And like I said, in my infinite free time, I'll flip this whole course around and we'll start with primes and drop them and be done with it. Anyway, so these are just plots of what happens to different tissue compartments, right? Different tissues have different T2s. How does that transverse magnetization decay as a function of time? And again, the imaging experiment is all about playing an RF pulse. So in this case, let's assume we've generated the maximum amount of transverse magnetization in some normalized space. It's 1. How do I generate the maximum amount of transverse magnetization? Look at RF pulse. 90, right? I got to tip down, right? So assuming the initial condition is equilibrium straight up, I play a 90, I have the most transverse magnetization. And so now again, I can time my imaging experiment. We'll talk about how to do that in the sort of coming lectures. But depending on how I time that experiment, I'll get very different contrasts. If I try to take a snapshot pretty quickly after tipping everything over, I haven't had a chance for that contrast to develop. There's no separation in those T2 signals. This is part of your homework problem, right? And so the image contrast here is arguably pretty flat. And then as we go to longer and longer, in this case what are called echo times, as we wait longer and longer, we don't form our images for, in this case, 235 milliseconds. At that point, there's a lot of separation recovery of different compartments, and that consequently gives you contrast. Now, the thing that's a little not clear, or maybe several things are not clear, but one thing that might not be clear is how do you capture the longitudinal or the transverse magnetization? Right? I've said several times that we have a coil. That coil is sensitive only to detecting which component, longitudinal or transverse. It's only sensitive to capturing the transverse component, right? So how in the world are you going to capture this signal? Ideas? How are you going to capture what's happening to the longitudinal magnetization? Gradients are going to help with imaging. Yep. But how are you have magnet, in this case, right, if I played an inversion pulse, and according to the equations of free precession, right, so if you go back here, this equation says my MZ component is just going to recover like these curves, right? And depending on how much time, it'll go through 0, and then we'll just keep going up. So according to this expression, how am I going to sample this magnetization thing?
You do an inversion pulse, wait a bit, and then send another pulse that moves back to 90 degrees, and you can look at the change.
That'll work, right? And so imagine you've tipped your magnetization all the way down. It's actually inverting along this mc direction, right? That's all this equation would tell you. How much mxy am I going to have during that process? So it's a little funky here to go through it. If I play an inversion pulse, right, how much mxy do I have after an inversion pulse? Right, so if I wait a few milliseconds, how much transverse magnetization do I have? Still 0, right? I didn't have any initial condition, right? After my inversion pulse, there was none. Then all I can do is decay. I'm never going to get transverse magnetization under those sort of perfect conditions of perfectly inverting all spins, right? So if you want to sample your longitudinal magnetization, you have to do what Aiden said. You've inverted it, and now it's recovering, and so then you have to play another RF pulse to generate some transverse magnetization. You can do this all quickly, and at the point you generate that transverse magnetization, it reflects what was happening on the longitudinal axis. It's tricky, right? We'll revisit this several times. We'll talk in the next lecture about saturation and inversion pulses and how they themselves give rise to contrast. So just kind of a heads up before this is happening. Yep. So here's where we sort of are in this class, right? It's week 3, at least according to this, we're 3/7 of the way through. And the idea that we talked about in the last lecture was how does B1 help us generate transverse magnetization. There's a lot of mathematical details that we're going to have to set aside for a little bit. We're going to get to them, which is how we sort of ultimately form images. Today what we're going to talk about is gradients. And one of the main things you'll remember, hopefully today, is that the gradients are used for encoding. Right? One of the principal applications, principal reasons we need so-called gradients is to do what we call spatial encoding or spatial localization. You need gradients to build images. They're one of the key ingredients. And in fact, that's really what the 2003 Nobel Prize was all about for Latimer and Mansfield. Latimer wrote the book we normally use. Mansfield did some really outstanding work, obviously. And it was mostly with regards to using gradients to generate images. So again, as always, there's some learning objectives, some things you can go back to understand what I think is important about this particular lecture. So we'll step through this kind of like we have, excuse me, with some of the other hardware components. Talk about sort of what's the underlying hardware, how does the hardware sort of nominally work, discuss some of the mathematics, work a little bit on the board, and then at the very end of the lecture, we should have time. I think this is a little on the shorter side, and we'll have some time to talk about that one as well. So this is a hardware teardown that we've used before, different hardware components. In the middle here, I have labeled a transceiver. What's the transceiver? What's it used for? Two possible things.
Transmission and receiving.
Yeah, so transmitting what? Yep, so this is the transmitter for the B1 pulses or RF pulses. And as it can transmit in the radio frequency range, it actually works as you can turn it off in the transmit mode and switch it to be a receive mode antenna. And so as a coil, it can actually receive the MR signal as well. Turns out it's not a great receiver because it's not that close to the body, right? It doesn't have great receive characteristics, and it's designed really to be a transmitter. And it's oriented such that it's focused and centered to be sort of most homogeneous, most active right at isocenter, right? The 0, 0, 0 coordinate of the scanner. And that's going to, today we're actually going to start using those coordinates. So we want to remember that isocenter is 0, 0, 0. It's the middle of the scanner. What we're really going to talk about today is really the gradients, right? And so we have the Z gradient shown in green, and that we'll talk about sort of why it's organized or put together the way that it is a little bit later. And then we also have the X gradients, which you see in red. There's sort of 4 sort of coil elements to that. And then we have the Y gradients, which are sort of rotated, but hardware design is very similar to the X gradients. But again, there's 4 components to that. And they might look rather big, they might look rather large. The idea is that there's a lot of, they will generate a lot of other stray fields that we don't care about at all. But importantly, right around the isocenter, in the middle of the magnet, they'll be generating the fields that we do care about, which are linearly varying, linearly spatially varying magnetic fields. You'll see it in the map shortly. We had an installation. I like showing you guys these things, right? So we had an installation here at UCLA. This is probably 5 years ago now. And so this is sort of what it looks like when before the patients get there. And so this is the back of the scanner. The patient would enter in on the table, sort of coming in this way. A couple different things to sort of point out. On the top end here, these are the power supplies that are running the current and the voltage to power the gradients in the first place. Very thick gauge copper wire, and you'll see why it has to be so in just a second. And then this circular kind of element that's also green, it's a variety of things, but it's mostly the gradient coils, which is principally what we're going to talk about today. And the gradient coils actually require very high voltage, require very high current, and consequently they're water cooled. And so all these cables that are sort of pouring out the left and the right, those are water cooling cables, so they take chilled water as whatever it is, 4 Celsius, and cool the system pretty continuously. Really stable, really pretty amazing engineering design, actually. We talked about it a little bit before. You can see these sort of slots, these trays here. Those are the trays that you could slide in and out to help make your B0 field more homogeneous. So if you turn off the field, you can pull out those trays. You have to turn off the field because they're full of these ferromagnetic cards, right? And then you can redeck it. You can put in different cards, slot it back in, ramp up your field, measure it, see that it's within specification. Okay, so what do we know about the gradients? Well, I said this a little bit earlier, but the primary function is to encode spatial information. And for now, that's the main thing to remember. When we get into spatial localization and image formation, you'll see that there's 3 main components of that. We have to select a slice that we care about, and that could be any possible slice, oblique slices, double oblique slices, coronals, sagittals, axials, whatever. You have to excite a slice. And once you've excited that slice, we need to extract imaging information from it, and we'll do that in 2 steps. One's called phase encoding, and one's called frequency encoding. This lecture is not going to get into phase encoding and frequency encoding, but it's a good thing to keep in your sights for what's coming in a couple weeks. Lots of secondary functions. There's other things that the gradients are useful for. We can use them to sensitize or desensitize images to motion. We'll learn in some of the last lectures how we can actually measure things like flow. We probably won't talk that much about diffusion. We can also measure displacements of deforming tissues and things like that. There's various ways in which gradients can be used to help minimize artifacts, using what we call pressures and spoilers. And you'll see it a lot when we really get towards the imaging aspects of the lectures. How the magnetization can be rephased or dephased according to sort of what we need to do. Getting ahead of ourselves a little bit there, the main thing to remember today is that the gradients are really for spatial localization. So for the B0 lecture, the B1 lecture, and now the gradient lecture, there's a slide that kind of mimics this. It says B0 is, B1 is, gradients are. And so what do we know about the gradients? Well, relative to, say, the B0 field, they're small. They're less than 5 Gauss per centimeter. So when we talk about gradients, what do we mean? We mean magnetic fields that have a gradient in space, and in fact, a linear gradient in space. That's what we call gradients. And so because they're fields that vary over space, we measure their units in terms of things like Gauss per centimeter. You'll see other units as well. Sometimes it's Tesla per meter, but nominally it's field per distance. What does that mean? Well, they're generally small fields. Why do I say they're small? Well, you can turn on a gradient, and the gradient might generate a field strength of 5 Gauss per centimeter. So every centimeter away, you go from isocenter, it's 5 Gauss, and another centimeter, it's 10, and 15, and 20. And so for a field of view, that's about 30 centimeters. So 30 centimeter field of view is plus minus 15, right? Just multiplying the distance by the gradient field strength, you'll see that you get about 7.5 millitesla. So we've got B0 field strengths at 1.5 Tesla. We've got, what are B1 field strengths? Microtesla, right? So we go from Tesla to microtesla, and then gradients are small. They're in between at millitesla, at least nominally millitesla. They're spatially varying. We talked about that a little bit already. And at least as we'll treat them in this class, they're linear, right? Now, every system has imperfections. I'll point to a couple today just so you have a heads up about it. But we'll treat them mathematically as being perfectly linear. So certainly makes our life easy. They're going to add a field component to B0, but they're going to add to B0 only in the z direction. And this is a really important distinction. We'll talk about having x and y and z gradients. X gradients don't generate fields in the x direction. They don't generate fields in the y direction. A z gradient doesn't generate a field in the z direction. Well, it does generate a field in the z direction. So when we talk about it mathematically, you'll see. But the B0 field and the gradient fields are magnetic fields that only point along z, only point along k. And we'll see what that looks like and why that's the case. They're time varying. So we can turn these gradients on, we can turn these gradients off. Is B0 time varying? Not for this class, right? Is B1 time varying? Very much so, right? You have that pulse envelope function if nothing else, but then inside of that is this megahertz, right, frequency signal. So these are time varying, but they're time varying on the order of like hundreds of hertz, or maybe thousands of hertz, no, tens of kilohertz. We'll talk about a parameter called the slew rate. So on the bottom here, we have a diagram of what we call a gradient waveform. So we can turn gradients on, we can turn gradients off. But it takes a finite amount of time to turn the gradient on to reach some amplitude. And so this is a typical timing diagram for a gradient pulse. A gradient takes a finite amount of time to reach its maximum possible amplitude. We don't always use the maximum, but in this example we do. And you can only sort of rise to the maximum at a particular rate. And we call that the slew rate. And so the systems that we have, the MR systems that we use, and the ones we'll talk about in this class, they have a specified Gmax. This is something that, like, when I'm looking for new scanners, I'm looking, wow, what's their Gmax, man? It's like shopping for a car and horsepower or something, right? So you want to know what their Gmax is, and you want to know what their slew rate max is. And we'll talk about sort of how these things play into safety and what it really means for imaging a little bit later. The typical max slew rates are on the order of, and units are a little bit of a thing here, but oftentimes reported in millitesla per meter per millisecond. That's the same as, you can drop 2 milli, so Tesla per meter per second. So about 150 to 200. And there's some limits on all of these things that we'll talk about a little bit later. But get comfortable with the idea of having an amplitude to the gradient that you can turn on, and then a slew rate, the rate at which you can reach or get to that amplitude. Now this doesn't mean, you'll see this doesn't mean that magnetic field has a particular amplitude. This means the gradient has a particular amplitude. And so that's going to be adding a linear variation of the magnetic field with a particular gradient strength. We'll see it in the math just a little bit. Of course, it's a magnetic field, and this can actually add or subtract to the B0 field. So we can oppose the B0 field and actually tune the system down a little bit, or we can superpose with the B0 field and actually make the field go up a little bit. There's different reasons why we might do one or the other. And then mathematically, it's parallel to B0. And I said this a couple times, but gradients are not fields perpendicular to B0, right? What's the one field that we use that is perpendicular to B0? B1, right? So B1 is in the IJ plane. Gradients in B0, or at least as we treat them, strictly in the K direction. Okay, so let's talk a little bit about the hardware for the Z gradients and the XY gradients. So typically we use what's called a Maxwell paracoil. We saw it in the first diagram. It's basically just 2 solenoids at either end of the scanner. And that alone will produce a pretty linear field variation along Z. You've seen what a solenoid can do, right, in your current homework assignment. If you put together 2 gradients, separate 2 solenoid coils, you can actually get a quite linear field in between those 2 systems. So these are sort of symmetric about isocenter with isocentricity somewhere in the middle. Very uniform fields along the XY plane as well. So within the plane of the solenoid, right, that's a very uniform field. And to generate these fields, then you would run currents equal and opposite in one coil versus the other coil, so that they oppose each other. And so what's the principle behind that? This is the Maxwell paracoil again. If I run current through this coil at the top here, I can generate some delta B0. I can add to my B0 field. And if I run current in the opposite direction on the bottom here, I can slightly oppose my B0 field. And so what that means is I have a gradient in magnetic field strength, right? I go from B0 minus delta B0 to B0 to B0 plus delta B0. So I have, in this case, a linear gradient in my B0 field strength. And that's exactly what gradients are supposed to do. X and Y gradients are a little bit different. They're typically saddle coils, or what are called Golay paracoils. Only, you'll see the diagram in a second, but it's only the innermost turns that produce the gradient field that we care about. We'll be producing sort of stray fields at other ends of the scanner. They exist, but they're not sort of important to us, so to speak. And those X and Y gradients are really identical except for rotation, so the hardware design is really similar. And it depends on the exact diagram, but you'll have one coil producing a positive delta V0, and then another coil producing a negative delta V0. And so this is sort of the system diagram for that. And the background is the actual wire that's laid out for generating this Golden paracoil. And then in the foreground, sort of the wire diagram looks the same. But again, the idea is if this is the z-axis of my scanner, right? If this is the z-axis of my scanner, and this is maybe the x-axis of my scanner, then by energizing these coil elements, I can have a lower field, say at the posterior part of my scanner, the nominal B0 field in the middle of my scanner, and a higher field strength at the top of my scanner. And so I have a variation in field strength along x. So there's a variation in field strength along x, that's an x gradient, but the direction of the magnetic field at all points is in the B0 direction, or the z direction. Okay? So the gradient is x, but the direction of the field is z. Again, let's see this map a little bit. So just sort of by scale, recognizing sort of where the gradients active, what area they active over. The gradients, as you remember, sort of embedded sort of outside of the table where the patient themselves lie. And they're linear over about 50 centimeters at isocenter. The best gradient systems are at linearity over 50 centimeters. And even the linearity is still even so-so. I'll show you a picture in just a second. But ideally, and at least for this class, we'll treat them as linear, and they're effective over volumes of about 40, 50 centimeters at isocenter. So the whole MR system is really designed to have a highly effective uniform fields of all kinds right at isocenter over that approximate volume size. This is sort of how in the background there, at least you can see how the whole system kind of comes together. You'll have an MR room where the coils themselves lie. Those really giant, they're sort of as big as my fingers, copper cables that are running, say through the ground or the ceiling out to a room. This room is outside of the MR suite. And these are the gradient amplifier cabinets. They're not of themselves noisy or whatever, but a lot of the water cooling is happening there. That's where the power supplies themselves are actually found. Okay, so what do the gradients actually do to our spin system? So this is we have no gradients turned on. So with no gradients turned on, then we expect to have V0 at all, say, Z positions. And so that means we expect to have the direction and magnitude of B0 field to be the same everywhere. So in these diagrams, the length arrow is going to indicate the strength and direction of the local field, right? And so if the field is the same everywhere, then the Larmor frequency is the same everywhere, right? That's what it's B0 that governs what the Larmor frequency is. So what happens when we look at precession? We just would expect that everything is just going to precess at the same frequency, right? You see the same B0 field, then all of our water spins are just going to do the same thing. So something you're familiar with already. Now the slightly more interesting case is in the presence of z-gradients, right? So here we have a z-gradient that we've energized. We've run current through it. That current is, for this example at least, just on, right? And in doing so, the way this bottom coil is built to that top coil, it opposes the external B0 field. The effect of both gradients is sort of nothing exactly at isocenter. We'll see that in the math in just a second. And as we go past isocenter, then the second coil is actually superposing a positive field. So we get this linear variation in magnetic field strength from say, foot to head. So what's that going to do to our spin system? Well, mathematically, we can see it for the first time on the bottom here. The Larmor frequency is going to depend on gamma, of course. It's going to depend on B0, of course, but also this additional magnetic field that we're applying. And the additional field that we apply in this case is the gradient strength GZ, just on the position. So how far away are you, right? So what is my Larmor frequency going to be at isocenter? Well, isocenter just means Z equals what? 0, right? So you just get back to that condition of having simply the B0 field. And so the expectation, hopefully, is this, that when you energize the gradient field coil and you look at the precessional frequency, you're going to have lower precessional frequencies, say, at the foot, intermediate precessional frequencies in the middle, and then it's higher, faster precession at the foot, at the head of the scanner. And it all comes out of this dot product. What's the magnitude of the gradient you've turned on, and how far away are you from isocenter? So we can talk about X gradient, right? So the X gradient shown sort of with the red lines there. The X gradient, when we energize it, is going to result in, say, the left-hand side having a slight decrease in magnetic field strength, the left-hand side, and the right-hand side having a slightly higher magnetic field strength. And so we can see we get this left-to-right gradient in magnetic field strength. It's left to right, so it means we've turned on an X gradient in this case. And so here's an example. And now we've actually changed the frame a little bit. So this is the first time I'm showing it this way. So what's shown in the middle there is the scanner, obviously. And then we have a gradient on the left and the right side. The spins, however, are processing. We're watching the precessional behavior of the spins in the rotating frame. So what happens to spins in the rotating frame at isocenter? They appear to not precess, right? Everything's at Larmor frequency, and so we don't see their precessional behavior, if you will. When I turn on an X gradient, though, I'm causing some spins to go faster, causing some spins to go slower relative to the Larmor frequency. When I'm in the rotating frame, that means that isocenter is stationary, so some spins are going to go counterclockwise, and some spins are going to appear to go clockwise. So here, the animation has just been switched into the rotating frame. Does that make sense? Because I haven't shown it that way before. So when we demodulate what's happening because of the B0 field, there's no apparent precessional behavior for on-resonant spins at B0. And then they go clockwise or counterclockwise if there's an additional field, and in this case, it's the gradient field that's been turned on. So here's another possibility. We can turn on, sorry, the animations are a little jerky. We can turn on, in this case, a Y gradient. So the Y gradient we usually think of as an anterior and posterior gradient. And again, the precessional behavior of the spins is shown, so that you have no apparent precession in the rotating frame at isocenter. And as you go more anterior or you go more posterior, you see this clockwise or counterclockwise rotation of the spins. And so the gradients subtract or add to the B0 field along a specific direction, right? Along the X or Y or Z direction, depending on whether it's an X gradient, Y gradient, or a Z gradient. Okay, so Shift 205, I probably use the same or a very similar slide. Let's say I want to manipulate my background field, right? Rather than having it be homogeneous everywhere, just B0, I want to impart this kind of spatial variation in my field. What kinds of gradients do I need? X and Z, right? So how do you know you need an X gradient?
The X gradient left to right, so increasing as you go left to right.
Yeah. So going left to right, you can see there's a change, a linear change in magnetic field strength, right? And then how do you know you need a Z gradient?
You're seeing change from bottom to top.
Right. So now so again, just saying it loudly enough that maybe the video captures it, but then from, say, foot to head, you can see the vectors that represent the magnetic field strength are getting larger. So the interesting thing for this example is if you look along this diagonal, right? So, yeah, you can turn this on. So if you look along that diagonal, you'll have a set of spins that have the same precessional frequency, right? You've turned on a Z gradient, green. You've turned on an X gradient in red. But those spins, the orange ones along that diagonal, the net fields that they see are actually all the same. So they're being sort of acted on in slightly different ways by the gradients, but the net effect is the same. So what does that mean about their precessional behavior, precessional frequency? It's all the same, right? So that's kind of interesting, right? Because that means I can turn on gradients in different combinations. Any linear combination of X, Y, and Z, I can generate what we call a plane of spin isochromats, spins that have the same frequency behavior, right? And so that's actually getting at this idea that MR is able to do arbitrary imaging planes. I can turn on gradients in any linear combination. I can steer this plane of isochromats around. I can make it purely axial with a Z gradient. I can make it purely, say, sagittal just by turning on the X gradient. Or in this case, I can make it oblique by turning on an X and a Z gradient. So we haven't gotten all the way to slice selection yet. We'll learn about it later. But if I can make a slice or a plane of spins have the same precessional frequency, I can hit it with an RF pulse with that precessional frequency, and those are the spins that will get excited. And spins that are at way off resonance, whether they're low or way off resonance because they're high, they effectively won't see the RF pulse and won't be excited. So that's your first insights, at least in this class, to how this process of slice selection works. So this is just another example, really, of the same. If we look at a set of spins, again in the rotating frame, we've cut through our subject axially, and we're talking about how could we possibly energize or excite those spins. We'd have to turn on both an X and a Y gradient, and then have an RF pulse that was tuned to the rotating frame frequency, and we would hit exactly those spins, and in principle not the other spins. So simultaneous gradients create an arbitrary, what we call isochromatic plane, or a slice, if you will. And it's good to remember that you can turn on these gradients independently. You can turn on any gradient at sort of any point in time.
So if you move like one diagonal down, it's the same exact concept, but shifted from the center.
It's the same concept, yeah. So let's say my B0, let's say my externally applied field is B0. Then in this case, I've added some gradients. So my RF pulse to excite this slice has to match B0. So it's just gamma B0, right? If I turn my RF pulse frequency from gamma B0, which we usually just call like omega 0, I can make it slightly higher in frequency or slightly lower in frequency, and I'll just be moving to excite a different parallel plane. So I can tune that RF pulse, that what we call the center frequency of the RF pulse. That's one way that we steer around the imaging plane in MR. There are other tricks you can play with the gradients as well. And ultimately, it's a combination of the RF pulse that you've used and the gradients that you've chosen to apply that will dictate which slice you select. This is important. It's important because I thought this when I was first learning MR. Now it's wrong. And so gradients don't do this, right? Gradients don't, at least as we treat them in this class, we'll talk about some little exceptions later, Maxwell fields and stuff. But gradients aren't changing the direction of the B0 field, the direction of the externally applied magnetic field, right? They're adding or subtracting in the K direction, the Z direction, and they're adding or subtracting gradients in the X, Y, or Z direction. So conceptually, you gotta get that right, because I don't want you having that sort of confusion in your head. So that's definitely not what happens. Okay, so that's kind of for the most part, kind of qualitative treatment of how the gradient system sort of is put together and what its effect is. We'll talk a little bit about the mathematics of it, and then I think we might do this for a bit and then take a break. So at least one more chunk of slides here. The sort of mathematics for this can be a little clumsy, but we're going to drop most of it pretty quickly. So you basically heard me say it already, but gradients are a special kind of inhomogeneous field whose Z component varies linearly along a specific direction that we call the gradient direction. So what does this all say? On the left-hand side here, you have a B field. We always use B as B fields. We usually subscript it as B0, B1, and here B gradient. So this is the B field induced by the gradients. And we've already said, but they only point along the Z direction. They only have a Z component. But they can vary along a particular direction. So this could be the X direction, it could be the Y direction, it could be the Z direction. So your B field, if you think in terms of fields, varies with X, Y, or Z. On the right-hand side is the more typical expressions that we'll really use in this class, which is to say we have a particular gradient amplitude for a particular axis, what we call Gx, the amplitude on the X direction, or Y or Z, and then it's multiplied, or in fact it's a dot product with the distance from isocenter. And so our distances from isocenter are signed, right? We have positive different distances and negative distances. Isocenter is the 0, 0, 0 coordinate. And so it's really the dot product between the applied gradient and the position you care about. You know, what position you care about depends on the problem, but that will tell you about the magnetic field at a particular position. Again, we're really going to mostly just use the expression that looks like what we see on the right-hand side, but it's good to remember that the product of the gradient, Gauss per centimeters, and distance gives us a unit of field strength. And so there's three different gradients that we could talk about. Every system has these embedded. We have X gradients, so-called X gradients, Y gradients, and Z gradients. And so on the left-hand side here, you see kind of what I'll call a typical gradient waveform, right? We can turn the gradient on at some point in time. It's on with sort of constant current, constant magnitude, and at some point in time we turn it off. And we'll see these kinds of timing diagrams a lot in MR. We'll turn gradients on, relatively constant, and then we'll shut them down at some point. What's happening to your spin system, or what your spin system cares about, though, is the B field, right? And the B field coming from the gradients themselves looks like the gradient amplitude multiplied by position, right? So if you're at isocenter, so this point right where it's crossing 0 would be isocenter, and if you're negative x with respect to the isocenter, then your B field is slightly opposing B0. And if you're positive with respect to isocenter, then the B field you're generating is superposing, adding to the external B0 field. We can look at different gradient strengths, and so this would be, maybe I was operating with the blue gradient, this is my maximum gradient strength, and now I'm doing something different with my experiment and I need half the gradient strength, that's fine. I can turn down the amplitude of my gradient, maybe I turn it on for the same duration. When I do so, the effective field generated by my gradient is going to be lower, in this case maybe by a factor of 2, right? So the slope of the magnetic field inside the scanner is going to change. If I turn this gradient off entirely, then the B gradient, or the B field from the gradients just goes flat. There's no contribution, 0 positions. So what does that sort of all look like taken together? We'll see expressions like this in different places, but again, we can turn on these gradient components, any one of them at any point in time. So it's really just a linear combination of what you want on X, Y, and Z dotted with the spatial position that tells you about the field strength at a particular position. So in the most general case, we just think of it as the dot product of a gradient vector. Gradient vector has components along X, Y, and Z. Position vector, so we'll see lots of position vectors kind of from here on out. R is just a position vector relative to isocenter. Right? You can have X, Y, and Z components to be somewhere in the scanner relative to isocenter. And then we've said it a bunch of times at this point, but the B field that you can generate as the dot product of the gradient vector and the position vector is always going to point along the K direction. Not sure how it's different. I guess just adding the two fields together, right? So the gradients contribute to the total B field, but again, only along the Z direction. So we have B0 along Z, and then this dot product along Z as well, in the K direction. And the gradients can be functions of time, right? We turn our gradients on, we turn our gradients off. But the B0 field is, again, it's a constant time field, so we don't usually show as time varying anyway. So what are the important things to remember here? Well, probably two things. The gradients are linear, or at least we treat them as such. And the gradients generate fields that point along Z. Those would be the two most important things to know right now. But of course, there are imperfections, right? This isn't always and strictly the case. So the gradients aren't perfect. I just want to show you sort of what the limits are here a little bit. So the gradient coils, I don't know, the engineers would probably say they're perfect. But the physics of the problem leads to some imperfections. In particular, you can get what we call spatial gradient nonlinearity. So the gradients don't generate a perfectly linear field, they generate a nonlinear field. We want it to be perfect, but of course that's hard. And the consequence of that is, you'll learn later that the gradients are really important for image formation. And we assume, in general, a linear mapping between position and frequency. You can see today already that we can manipulate frequency now, right? We can turn on gradients and we can manipulate the Larmor frequency. And so you can start to get this idea that, oh, okay, if that spins at a particular frequency, it's starting to tell me what its position is. And that was kind of the real insight that Latimer and Mansfield had, that you could encode spatial information by manipulating the range of frequencies, what we learn about in Fourier imaging later. So the bottom line is, uncorrected, our gradients are not perfectly linear. And if we do an imaging experiment with our sort of just installed gradient systems, we'll get images that look like this. This is a coronal image through a person, and you can see the anatomy looks a little unusual. The hips are pinching down a lot, the legs are getting really small. Maybe the upper anatomy is pinching in as well. There's some overall distortion. And that's because that linear mapping between space and frequency is not perfect with our slightly imperfect systems. And so behind the scenes, the manufacturers have to deal with that. They have to do warping, right? They have to figure out how to take their nonlinear images and warp them back to a linear space. How much does that matter? Depends who you are, right? As a diagnostic radiologist, you don't probably care too much, right? Meaning you can understand a patient's anatomy and what's going on pretty well, even in the context of some nonlinear warping. If you're driving treatment, interventional treatment, or cancer therapy, then you probably really care about position. right? Because you want to be treating the right target tissue. So then these kinds of mappings between, you know, the natively nonlinear back to the real anatomy, real geometry is actually quite important. So we have spatial imperfections. We also have what we call gradient delays. So we turn these gradients on and off. The timing between turning those things on and off might be, there can be delays in the system, so we don't get exactly the behavior we want. I'll have a good example to show you what that looks like. But another possibility is generating what are called eddy currents. We'll talk about eddy currents more later, but what it looks like in imaging is if I turn on really strong gradients in different directions, so I can turn a gradient on in the x direction, or in this case the y direction, you can actually get your images to distort if those gradients are strong enough. So there are ways in which our gradients are imperfect, is what this is to say. But again, for this class, we'll treat them as being linear over the field of view we care about. I won't spend a lot of time on this. We certainly could. One of the imperfections in the gradients comes from Maxwell's equations, right? So I've told you that when we turn on gradients, we only get field components in the z direction, and physically that's actually impossible according to Maxwell's equations. And so when gradient fields are applied, other fields are unavoidably produced, which is what the Maxwell equations rather capture. And so the B field has to obey this divergence law and a curl law, and we make the assumption that when we turn on our gradients, that any x component of the field generated and any y component of the field generated is 0. But in fact, these end up being non-zero. And depending on exactly what you're trying to do, they could cause problems. So again, just especially maybe for the physicists, something to keep in mind. That the details can matter, and in fact, we do make Maxwell field corrections in a lot of the stuff that we do. Okay, so this is a summary slide that links back to kind of the, you know, each of the hardware lectures at this point, right? And I think it's really good to think about the assumptions in MR, right? What are we actually going to be assuming through most of this course? So when we think of the B0 field, we're assuming it's perfectly uniform over space, right? That it's B0 everywhere by design. And we refer to that as B0 homogeneity. And we also assume it's perfectly stable in time, right? That B0 is just on and constant over space and time. That's very different from the B1 field, right? B1, we also want it to be perfectly uniform over space. We refer to that as B1 homogeneity. We want to get the same amplitude of the B1 field. And we assume it's temporally modulated exactly as we specify. So in your homework assignment, you're hopefully appreciating the importance of sort of frequency and of the magnitude. What happens to our flip angle if our B1 field is not homogeneous? Is our flip angle the same everywhere? No, right? So flip angle matters, right? If you are designing a target of, you need a 90-degree flip angle, but you have B1 homogeneity, you're not going to get a 90-degree pulse everywhere. So it's not, the system's not going to be doing what you have in mind, and that will inevitably lead to artifacts. And then for today, then we introduce this concept of the gradient fields, and we assume, right, this is the assumptions, that they're perfectly linear over space. We refer to that as gradient linearity, that they're temporally modulated exactly as specified. We can turn them on, turn them off exactly as we have in mind, and that they don't, in fact, induce any of these Maxwell fields. We didn't work out the terms there, but these additional fields that physics dictate will exist. So with that, happy to take questions, but we'll take a short break and then come back and move forward. So let's take 5 minutes. Send me the correction and let me look at it carefully. Yeah. Oh, well, yeah. If I made a mistake, don't worry about the homework. So we'll catch that and make sure people get a good credit. So that's okay. But I'll double check exactly what you're saying. That's fine. Cool. Thank you. Yeah. Yeah, sure.
So I'm sorry, you're saying it's not possible to have this, or it's not?
It's not what we want. I didn't want sort of this inadvertent misconception that an X gradient like, tilts the field,
Right.
and a Z gradient sort of tilts the field or something like that.
So to be able to align perfectly on Z axis, you have to basically modulate the X gradient and Y gradients perfectly.
Well, so I would say a little bit differently. I would say that when we turn on the X and Y and Z gradients, they're only changing the amount of B field in the Z direction. The B field always points in Z. So I can turn on an X gradient and I can make my B field do this. I can turn on a Y gradient and make my B field do this. Or I can turn on a Z gradient and have my B field sort of do this. But it's always pointing in this direction. And I didn't want people to think that, oh, I turn on an X gradient and the field points this way. The Maxwell fields actually cause it to point off axis at the right time.
Okay, so that's because that's why this graph we have these coils basically, so the center of these coils is pointing really always.
They are.
The placement of these coils basically essentially avoids have the magnetization pointing in the wrong direction.
Yes, and if you look back, this one here, so the sort of active elements are really, there are coil elements here because you have to have this current path, but it's really these ends of the Golay pair that are generating the field that contributes to, in this case, the X group. Yeah, sure.
I have a question.
Oh, you said like, why is the brain so distinct relative to? I think it's just a coil actually for this example. So we haven't really talked about coils too much yet, but like with a head coil, right? The coil is really surrounding the head, and it's not a neck coil. So then you just don't pick up good signals there. We have head and neck coils if you want to do like neck imaging and so forth.
Well, do I do see
Yeah, it's possible. Yeah, but mostly I think it's coils.
So for I think on question 1,
Yeah.
I was just doing, well, not exactly how you thought, but using additional coils like you were saying. So I was doing multiple coils, but I was using just a whole lot of very small coils.
Sure.
But since there's so thin, I know the equation you gave us for the field really only works while they're inside the coil, so I had to bring it to the length of the coils. I was wondering if I should just not doing that because I mean it, but
Oh wait, so what did you do?
so I have a bunch of very
Like
thin
short coils.
Yeah, so I originally
Yeah.
so I was originally trying to have like just additional coils to kind of even it out, but it's not working or it's too complicated. So I did a bunch of small ones.
Yeah.
So it has a really good homogeneity, but it's because it's the field measure for each one isn't long enough to decay significantly. So it's really noisy, but just very
It's like bouncing
small.
up and down.
Yeah, it's a, the
Yeah.
plot is just a blue block because it's just up and down so much.
Oh, I see.
But that's like the entire.
But you're
field.
if you have a thin coil, are you counting the field outside the solenoid at all?
No,
You're
because
just
that's
counting it within.
because that's supposed to be fixed. I was like,
That's-
I
that's
know
a
this
very-
isn't right in real life,
It's not- yeah,
but I
yeah.
don't know if it'll accept
No,
because
no,
that's
that's
okay.
I'll be right back, guys. I'm just doing
That was Nathan Ventures. Oh yeah, they found out that
I feel like all the stuff that took me a long time were not things that were supposed to take like a long time. Like other components. Because like, okay, I do it and I'll do it, and then the reason. Why? What notation am I doing wrong? And then you're just like, this function. Yeah. Working.
And sometimes it was just like a matter of,
Yeah. That totally happens. I could have another class too, where it's like I would divide by a factor and I would turn like a cubic thing into just square. Like it would just turn into like a block on a square. Like how? I'm dividing by a constant, and then I realized like the constant was just like large enough that I didn't see any increase or the part I wanted. So, like, no, I just changed the scale. I'm like, okay, there it is. I'm safe.
That's what we were trying.
Yeah, I think that's
It's like,
yeah, I did. Oh, yeah, just for this.
it's the normal moment, right? Everyone gets comfortable talking and then, sorry. Okay, so we're going to work through a little bit of mathematical understanding of what's happening with the gradients using a lot of the framework that we've seen before. So the example I want to work through here right now is discrete precession. This is going to be in the rotating frame. It's going to be with gradients. That's what this lecture is about. And then we're not going to give ourselves too big of a headache, so this will be moved out of relaxation. Okay, so the first thing we have to do, because we're working in the rotating frame, is think about B effective, right? What's the B effective for this particular problem? And so the sort of starting definition for that is just that we have omega root vector of gamma plus B root. And of course, what's going to be different in this problem relative to the other ones is what is the B root that we actually have and need to consider. And so we know what our omega root is. It's always basically the same for the systems we care about, right? We're demodulating the effects of that B0 field. And so on top here, we just have minus gamma B0 and then the k hat prime direction because we're in the rotating frame. And then that's divided by gamma. And so then the question really is, well, what's our applied B field? When we have the B0 field and the gradient fields, right? And so we know we have our B0 field. B0 is easy to deal with because it only points along K. K and K prime allow the rotating frame to be the same. Fortunately, gradients are really similar, right? And so we have our gradient vector. It's a vector because it can have these different X, Y, and Z components. They have to dot that with position, so where we are relative to isocenter. And the good news is all of that points along the k hat prime direction. And so what does that mean? Well, there's a bunch of terms there. Not a bunch, but the B0 terms are going to drop out. That's the demodulating of the B0 precessional behavior. And so the B effective in the rotating frame is just our G vector dotted with our R vector pointing in the k hat prime direction. Easy enough? So that's our B effective. Then we have to go back to our the block equations for what's going to happen to the spin system when we have that as our applied field. So I'll make a little bit of space here. And we have to go back to our the block equations, which are partial dm rho partial time equal to m rho vector, bulk magnetization in the rotating frame, times gamma B effective. And we said we weren't going to worry about relaxation, right? So I'm not going to consider that for this case. Why do I not care about relaxation? Well, oftentimes the gradient events that we use or concern ourselves with, they're pretty short in duration, milliseconds. In milliseconds, when relaxation is on the order of tens or even thousands of milliseconds, then we don't care too much about it. So for now, we'll ignore the effect. We did just define what our B effective is, and so this just becomes M rho cross G, or G vector, dotted with our position vector along the K. And so you've seen enough examples of this already to hopefully you recognize what we're going to do next, which is to take that expression here, the equation is really just the equation of motion without relaxation. And we'll write out the system of equations and we'll talk about solutions, right? And so on the left-hand side here, this represents three different equations. So what's happening in dmx dt, what happens to dmy dt, and what happens to dmz prime dt. That's just this term. And then we have this determinant operator, so we have the I hat prime, j hat prime, k hat prime across the top. Our mx, or our bulk magnetization components are always the same, so it's mx prime, my prime, z prime. And then the only thing that's different, say for this problem, although it'll look quite a bit similar to some other problems we've looked at, is that we don't have any B effective on the I direction. We don't have any B effective on the J direction. The only B effective component we have is on the K hat prime direction, and that looks like gamma G vector. Does that setup remind you of anything? Would it look like a problem we've worked on before? I think so. It looks a lot like free precession in the lab frame, right? So when we were talking about free precession in the lab frame, this term here was just a B0. So we actually know what the solutions to this business looks like. So we'll just write the system of equations and we'll jump to the solution. So this business here represents the system of equations, right? And if we carry out the determinant that's inside all of this, we can define our d mx prime dt would be equal to my prime times gamma g vector dotted with r vector. And then we have a d my prime dt equal to a minus mx prime dotted with gamma g vector dotted with r vector. So you can see that coupling again, right? We have coupling between the x and y components of the magnetization. Yep.
Did the gamma fall out in the second?
It wasn't supposed to. They don't just disappear, right? Thank you. So there's a gamma there. And I do appreciate you pointing it out. Too many mistakes. Okay, and then the last thing to write out is our d and z prime dt. And then if you carry out the cross product business, then you just get zero. And so these equations actually, that system of equations that we have right now, I said this before, but this looks a lot like free precession in the lab. So the good news is, I won't drag you through the solution. We can jump ahead a little bit and have an expectation. So what is that expectation? When you see that sort of coupled mx coupled to my and my coupled to mx, what's going to be happening to the magnetization? What kinds of solutions do we expect? We do, yeah. So here we have coupled ordinary differential equations, and we could go through the steps of decoupling it. And then if we did decouple it, we'd end up with a second order differential equation. And the solutions were like sines and cosines, and that's where we previously, when we were talking about the free precession of the lab frame, that's where we came up with this. We could see mathematically that it gave rise to the precessional behavior of the spins. So in this case here, the solution is relatively straightforward. I won't work through the same as what we did back in the pre-processional lecture. But you would get that there's a processional frequency that comes from the gradients. So we can talk about omega 0, we can talk about omega 1. This is the processional frequency from the gradients. It's a vector, and it has an axis about which the procession is acting. But in this case, interesting, the processional frequency is a function of space. And we write position vectors as our vectors, so that tells us where we are relative to isocenter. And the solution to that system of equations would tell us that the processional frequency that varies over space depends on minus gamma times our gradient vector divided with our position vector, and it's all happening around the direction. So the gradients cause precession, they're B fields. The B fields oriented along the k direction, so that shouldn't surprise us too much. The perhaps most interesting thing here is that they're going to give us precession that depends on spatial position, right? Depends on where you are relative to isocenter. What is omega g at isocenter? 0, right? So it's always good to go to those sort of simplest examples to maybe get an understanding of what's going on. And so this equation here just tells us that the precessional frequency varies with space. So that's important because it tells us that we can change the Larmor frequency, and we can change the frequency of precession by turning on a gradient. We turn on a gradient and the frequencies are different everywhere. What happens to the frequencies everywhere when I turn the gradient off? They just go back to what? Yeah, just back to like B0, right? So we can turn the frequencies up and then we can just shut them right off, right? And the time response is fast. The systems react very quickly to the applied magnetic fields. So this tells us how importantly, it tells us what's happening to what's happening to the frequency, right? There's another thing that can happen, which is what happens to the phase. So you have to picture that with the bulk magnetization, I can tip it over with a 90 pulse, right? Now, gradients can cause that bulk magnetization to precess more quickly, or in fact, kind of go the other way if we're thinking about it in the rotating frame. So we can control the frequency. If we can control the frequency of the spins, we can also control the phase of the spins. And so by tipping the magnetization down with a 90, I can turn a gradient on, and I can give phase to the spins. I'll show this mathematically right now, but if we can manipulate the frequency, we can also manipulate the phase. Both of those are sort of essential concepts. So let's look at how we can get to manipulating the phase. And so we can define the phase that comes from a gradient. It will, in fact, vary over space, just like the precessional frequency varies over space. And it can develop or accumulate as a function of time. So the amount of phase the spin has will depend on things about the gradient. So what does it actually depend on? Well, phase is really just the integration of frequency. You have more phase the longer you exhibit or have a particular frequency. So this isn't even really MR physics at this point. We integrate from 0 to time some frequency function, omega g in this case, which itself varies over space and time. So that is a tau. So that's just the definition of phase that arises really from frequency. It's a general expression that's true of sort of any system, but now we're going to see how the gradients get sort of rolled into this business. So picture, if you will, gradient. And maybe this gradient is the terminal gradient on. It's going to persist for some period of time, and I'm going to turn my gradient on. And so this is just some time 0, this is some time t, and then this is just the gradient function as a function of time. So turn the gradient on, turn the gradient off. Just by substitution of this previous expression here, we get a new expression for the phase, right? which just says that we can integrate the minus sign, we can integrate from 0 to the, say, duration of the pulse, substituting in gamma, or gradient vector, which is itself a function of, say, time, dotted with our spatial position, which it could in fact be a function of time. Now, in the simplest, in a simple case, at least, we could let, for example, our gradient function just be some particular amplitude. So it's just saying that this here has some amplitude gx, and that it's on for some duration, in this case we're calling it t, and that our spin position, which could vary over as a function of time, that spins could in principle be moving around, but we'll just let this be some x position we care about. And so if we take the integral where our gx is constant and our position is constant, this just gets a little bit simpler. We'll say that the phase from the gradient really just depends on where you are in space and what time it is. It's just minus gamma gx dotted with your x position dotted with the duration. So what does that mean? Well, it sort of means a couple things, right? This here. So our spin phase, right? That's the phi g. Phi g, it's going to increase, right, under different circumstances. It's just an extension of what's sort of being shown in that expression there. But if we have stronger gradients, then spin phase is going to increase, so it increases with increasing gx. It's going to increase with position, and it's going to increase with time. It's a simple algebraic expression, right? What is it? All I'm trying to point out here is that the amount of phase you have for a particular spin depends on how far you are from isocenter, right? So spins at isocenter can't, in principle, accumulate phase from gradients. But if I'm farther and farther from isocenter, I'll have more and more phase, depending on how long I'm exposed to that particular gradient field. So if I have strong gradients for long periods of time, I'll get a lot of phase in my system. If I have no gradient turned on at all, I get no phase in my system. If my spin's at precisely isocenter, it's not acted upon by the gradients because the gradients don't generate a B field at isocenter. Right? You have to get distant from isocenter to see what it is. So what was the point here? The point was to show how through the block equations we can understand how frequency can become a function of space and how phase can also become a function of space. And those will be, when we get into imaging concepts, those will both be important ideas. Questions about sort of what we did mathematically here? I'm going to roll up a little bit, and we'll use this expression just to go through one example, and then we'll go back to the slides for a little bit. Yeah?
So if you redraw it in the XYZ plane, it basically, the phase would be moving in the Y, right? We're moving from your Y.
So if you're saying what happens to how does the spin move in the transverse plane?
Yeah.
So you're picturing this, I think. So this is my x, this is my y, and I have both vectorization. This is my n x, y.
Yeah.
Is that what you're asking? That you're saying where as a function of time, where do the spins go? Yeah. And so because there's that minus sign, we have these left-hand rotations, right? And so we'll see the rotation operators later, but it must be the case that this is going to rotate this way, right?
So that would be our phi then, right? The angle that.
Yeah. So I mean, it depends on what your initial condition would be, but as time is elapsing, then you're going to rotate in that left-handed way because there's this minus sign that always shows up that means that B field, any B field, causes a left-hand precession in the spin system. Yep. We'll see that show up when I get back to the slides too, so it shows up as a rotation. Okay, so so one more just example of sort of how this comes together. Let's see, I'll go ahead and water this just for space. So all I'm going to do is just make some simple examples from this expression, the last expression that we just, which is this. And so the setup is, let's consider a gradient. The gradient that I care about is one that I can move on, say, negatively. Sometimes we care about gradient areas because they capture sort of the product of both strength and duration, right? So we can say this is a gradient of area A. Maybe with my axis, that's the time axis, and this axis here is just what's happening to maybe my g-axis function. And then if I turn my gradient on in the negative sense for a while, maybe to an amplitude of minus gx, I can then subsequently I can turn my gradient on to be positive for maybe a period that's twice as long. And so this has an area of A plus area of 2A, and it has an amplitude that I want to associate with plus gx. So that's the gradient waveform that we care about, a gradient that's negative for some period of time, and then it's reversed in its amplitude. We can have positive gradients, we can have negative gradients, right? It's just the direction of the current that's swimming through the coil. And then I want to talk about what happens to the phase of a spin depending on the spin's position. Okay. And so underneath this, we'll make a picture of, or a plot that accords with the one that's above it. So as a function of time, what's happening to the precessional frequency from the gradient. And we're going to consider different spins. So the spins we're going to talk about is we'll have one spin that's at isocenter. We'll have another spin here that's at some positive x position. And we'll have another spin that's going to be, say, a negative x position. We'll consider each of these, if you will. And so we had two expressions. We had an expression for the omega as well, right? What is the precessional frequency as a function of spin. And so if you have a spin that's at isocenter, what's the omega g for a spin at isocenter? It's just 0, right? So it doesn't matter what gradient you turned on or what gradient you turned off. It's just going to have no effective omega g, right? So then the other thing to consider is what happens to, say, a position that's at plus x away from isocenter. So what's the frequency going to be at plus x away from isocenter? Is it going to be positive or is it going to be negative? It's going to be negative because we have this negative sign in front of it. So if we go up to, this is the expression that we're thinking about now, right? What happens to the frequency as a function of position? So this equation here, sorry, I'm just making it more clear. What we're plotting here is just what is omega g. It should just be a minus n times the gradient strength dot position. And so if we are a spin that's a positive distance away from isocenter, then we're going to have a negative precessional frequency. So it's no precessional frequency to begin with, and it's going to become a negative precessional frequency while the gradient is negative. And then what happens when the gradients turn positive? Oh, sorry. You guys are wondering what I'm doing, right? So Tyler was right? Because we started with a negative gradient, so two negatives make a positive, right? So I think I have it wrong in my notes. And so omega g for that spin that's a positive distance away will be 0 to begin with, and then it will go positive. And then when the gradient's turned over, then the omega g will go the other way. Does that make sense? So then we can talk about the other spin, which is the negative spin. It's also going to have no precessional frequency to begin with. But then when we turn on the negative gradients, it's a negative distance away with a negative sign. So this is going to go negative. Perhaps the slightly more interesting thing is what happens to the phase. So let's that make sense, what I was drawing for what's happening with the frequency? It's just a plot of what is the frequency as a function of time for different positions, 3 different positions. Yeah.
Is it supposed to be on an angle, or is that just to show?
Yeah, I just couldn't get it perfectly straight. Yeah. But I'm assuming my gradients here are just like blocks or like functions. And so then the related and last thing that we'll do here at least is just talk about what is the phase that comes from the gradient as a function of time. And this is where we get, I think, a relatively interesting result. And so we start with x, the spin that's at isocenter. How much phase am I accumulating as a function of time? 0, right? So it's the uninteresting sort of trivial case. It's just phase at 0. And let's see if I can keep myself straight here. So now we have this x, this spin that's at a positive x position. Initially, it's experiencing a positive precessional frequency. So we'll accumulate a positive phase. It's going to be 0 phase to begin with before the gradients are turned on. And the expression told us that we had just up here, top left corner, was that there's going to be a linear accumulation of phase. So that means the phase of the spin system is going to linearly increase the longer the gradient's turned on. And then the second thing that happens is we reverse the gradient. We go from a negative gradient to a positive gradient. So what's going to happen to my phase now? Is it going to go up or it's going to go down, right? It's going to go down at the same rate because our gradient amplitude is the same. So in the same amount of time, I should get back to, say, 0. And then, in fact, it will continue on because my gradient has additional duration to it. So that's the phase that's happening to that spin at the plus x position. So then the last thing to consider is what happens to the spin that's at a minus position. It's going to start off with, no phase accumulation, right? And now, which way is the phase accumulation going to go? Positive or negative? Negative, right? I have a negative precessional frequency, and so I'm going to accumulate a negative amount of phase and then head down that direction. That's only during the duration that the gradient amplitude is negative, and now the next thing to do is to change the polarity of the applied gradient, right? So now, which way is my phase going to go? Positive or negative? Positive, right? So it's going to start heading up to this point here, and in fact keep going until the gradient's turned on. So what's so interesting about this? Well, it's just one way of identifying sort of what's happening to frequency, what's happening to phase as a function of positions. We looked at the red spin, the isocenter spin, and the blue spin, if you will. And keep in mind sort of what's happening at, say, that particular highlighted position, right? This means I can turn on gradients, I can force my spins to fall out of phase with one another, right? So I can't do all 3 spins at the same time, but the red and the blue spin are going to be accumulating different amounts of phase as that gradient's turned on. And now I'm going to reverse the phase of that gradient, and they're going to come back towards each other again. And when they have 0 phase at that particular point right now, that means all spins will fall into alignment with one another, right? I could have chosen, for example, a different spin system. Maybe I could also draw it in blue, and if it wasn't as far away in x, it would be here, go down, and come back up like this. But all spins will be rephasing at that same time. Here I could choose another spin, and go up, not as much phase. Oops. Not as much phase, and then it would accumulate some phase to that same peak. It would zero out the phase at the same 0 crossing. And this is really cool, right? It basically means that spins at all positions will accumulate a linear amount of phase. And if I flip the gradient over and have it on for a strength and duration of A, right, I can bring them all back into phase with one another. If I keep that gradient on, then they flip past each other and they fall out of phase with one another. And we'll see this concept a lot in MR where we can dephase spins. We call this period where they're all getting accumulating phase, dephasing. And we can flip the gradient over and we can cause the spins to come back together again. We call that rephasing. And when they're all rephased at this point in time, they're all pointing in the same direction, that actually helps us generate a lot of signal. Now why you want to go through that whole madness of getting everything dephased and rephased, we'll get to later. But conceptually, keep in mind that we can manipulate the phase of the spins, dephase them and rephase them. Yeah? so that's what I had in mind to work on there, and then I think there's maybe a dozen more slides or something like that to work through. And then, we can talk about that homework for a little bit. Remind myself more in there. Yeah. Okay, so this is the expression that we just worked on. What's the phase that arises from the application of the gradients? The gradients have an amplitude, spins have a position, and it's their product that tells you how much phase you're going to have. This actually, the phase that comes from a gradient actually represents a rotation again. Tyler sort of asked for that example a second ago, which way are the spins moving in the transverse plane? And that's shown here. It's a rotation, again, about the z-axis, right? It has the same field orientation as the B0 field, so it has, in effect, the same effect on the magnetic field. You'll see examples of this. We haven't used it yet, but this is the homogeneous operators for the gradients, right? How can we generate a gradient operator that will have the desired effect on the spin system? And this is a slightly more complicated form that includes the integrals, just to say that it depends on the integral of that gradient waveform. How long is that gradient turned on for, and what's its amplitude history? And that'll give rise to the phase that will, that'll give rise to the phase that we use in this rotation operator. We'll see examples of this when we get to it later. It looks a lot like stuff that you guys have worked with already. We just have to take into account what's the field effect at a particular position. So this gradient operator takes in gamma, takes in the amplitude, takes in the duration, and then importantly takes in the position. We have to know what spin we care about. And then the product of the amplitude and position gives you the B field, and then the B field, if we put it into something like Larmor's equation, 2 pi gamma of the B field, multiplying them just by time, we get the phase. We get how far the spins will have processed as a consequence of the gradient. So I'll put this just as an example now. It looks a lot like the B0 operator. It just takes different inputs. I don't have the worked example for using it right now, but we'll see that soon. So at this point, you've seen this in slightly different forms, that we have these operators that we can use now. We can design the B0 operator, the B1 operator, the relaxation operator, and the gradient operator. There's not too many more operators that we need to simulate everything in MR that we really care about. We might introduce one more a little bit later. We'll revisit these. I'll try to put together a little bit more material that uses the relaxation operators and the gradient operators, but that's just sort of a heads up for what's going on. We talked a lot about what the gradients are. We talked some about how they're sort of designed. We haven't talked too much about the limits, so we'll talk about the limits of their design, and we'll talk about some safety, and then we're done for the day. So the amplifiers that drive these things are pretty impressive. They can generate about 500 amps and about 2,000 volts per axis, right? So you've got an amplifier on X, Y, and Z separate amplifiers. So pretty high current. The higher the current you have, the larger the Gmax you can generate, right? And we care, you'll see why, but later you'll see maybe it stands to reason that we want high Gmaxes for sort of the most advanced imaging applications that we can come up with. We need higher and higher voltage to have faster and faster slew rates. So how quickly we can switch the magnetic field from, say, that positive gradient, from that negative gradient rather, to that positive gradient depends on the slew rate, right? There's actual slope to those gradient waveforms. We can only switch so quickly. There's hardware limits, and we'll talk about some physiology limits in just a second. They're driven at really high raster rates, so we can drive them in something like, depends on the system, of 2 to 5 microsecond steps, so we can command the gradients to do things every 2 to, say, 5 microseconds. But we can only increase or decrease as long as we fall within the slew rate limits of the system itself. Back to just circuits that you've taken up before, the power for these systems depends on the power, the product of the current and the voltage. And we're talking about pretty high currents and pretty high voltages for these systems. And so this is a typical gradient waveform, and if we drive it at maximum, it can use as much as like a megawatt per axis, right? That's a substantial amount of power, so it's similar to what a Formula 1 concept car would use. What if we want to go faster? In MR, we usually oftentimes want to go faster. If we want to go faster, we have to take this gradient waveform and we have to make it shorter in duration. But if we need, usually what we care about is our gradient areas. So if we want to get the same amount of area out of a shorter gradient waveform, we have to go higher. So two things happen when our gradients get shorter, right? We're increasing Gmax, and Gmax requires more current. But we're also saying we need to get to Gmax in less time, and that means we need higher voltages or faster slew rates. So there's some real practical limits to the gradient hardware at this point in time, which is, as this last thing says, if I want to increase by a factor of 2, I have to increase my Gmax by a factor of 2, I have to double my slew rates by a factor of 2, and that combined action means that you need about 8 megawatts per axis. And then if you want to go even faster, then you end up needing, a small nuclear power plant just to run the gradients for your MR system. So there really are some practical engineering limits to sort of power delivery for these systems, at least with current designs. It's going to take sort of next generation something to get us to even better systems. So what's my point? My point is there are some genuine hardware limits at this point. A simple model for how these gradient systems work, this is just a voltage model for an LR circuit. And so the voltage that you need to drive, right? You have a gradient system on the right-hand side. It has a resistance, it has an inductance. And you want to jam a certain amount of current through it to generate the Gmax that you care about. We can talk about how much voltage you need, and it depends on the resistance, it depends on the inductance of this system. And so this is just one simple way of describing the voltage response for those systems, the systems that we care about. We can talk about the gradient strength. It depends on the current. So the more current you can generate, the more fields you need to create. And the scaling factor there is what you call the efficiency. So there's some eta, some efficiency factor that says how your current is turned into field. Differentiating that, plugging it into the above, you can get an expression that tells you that what your slew rate depends on, how it depends on your coil efficiency and the inductance and the resistance and the inductance as well. So what's the point? Well, when we're designing systems and talking about the operational specifications for the system, we think oftentimes in terms of the gradient amplitude and the gradient slew rate. So when we're commanding the gradients to do something, there's somewhere in the space of gradient amplitude and gradient slew rate. We can't have infinite amplitudes, we can't have infinite slew rates, so there's some pocket in this space that's relevant to us. So the dashed lines right now just tell you where the Gmax lies, just kind of arbitrarily. The maximum gradient strength you can generate depends on eta and the maximum current your system is capable of generating. On the other axis here, and it's maybe not super obvious, but there's a slope to this slew rate function that came out on the previous side. So we can plot out the slope of this slew rate response. The slew rate response actually depends on voltage, inductance, resistance, but also the gradient field that you're trying to generate in the first place. What does that mean? Well, it just means there's some lines in this space that box in the operational range for the scanner. So there is the scanner, if you know what its efficiency, inductance, and resistance is, you can only operate somewhere within this box in terms of what the system can actually generate. So it defines the operational space. Okay, so in principle, this is what is what I'll call hardware achievable. That the system that we have available to us, we can operate somewhere in that sort of realm. But we don't really want to design our sequences with terms of voltage and current limits, right? What you're going to learn about in this class is why we're going to specify a certain Gmax, why we're going to specify a certain slew rate. We don't want to be designing sequences in terms of voltages and currents. These are, this outside box is the voltage and current limit for a given gradient amplifier, basically. More practically, we have some different limits in place. And so this is what I'll call this inner box here is what we call sort of biologically achievable. Why? Well, on the left-right axis, you can in fact generate very, very strong gradient fields, and that won't have a biological effect. We'll come back to that in a little bit. The slew rate, on the other hand, if the slew rate is too high, you'll get what's called peripheral nerve stimulation. So if we try to ramp our gradients up too fast or ramp them down too quickly, that can actually lead to this sort of tingling sensation it's almost like your hand is falling asleep. We call it peripheral nerve stimulation. So the hardware limit is the outer sort of trapezoid, but the sort of biological limit, the maximum slew rate that's allowed and the talk about this a little bit more, but FDA puts limits on this, is actually somewhere inside that constraint. And so we really designed in the space of gradient strength and slew rates rather than currents and voltages. Okay, so I mentioned a little bit about gradient safety, and we'll talk about this. I think it's the last thing. So with gradient safety, there's two gradient characteristics that we really care about: the maximum gradient amplitude and the maximum slew rate. The maximum gradient amplitude, there's no reason that it should cause some kind of a problem. B0 is already pretty big, right? What was the contribution of the gradients to the field on the scale of what? Do you remember? Early on, we did this example of the position dotted with the gradient amplitude. We got fields that were on the order of microtesla for V1, like millitesla, right? So these are we're just adding millitesla fields to something that's already in the Tesla range. There shouldn't be any reason that we care about Gmax, really. We're not even close to B0 field strengths. And so it sort of bears out here in terms of if you multiply the gradients by the distances we care about, you're in the millitesla range. So it probably shows up somewhere there. If we talk about the Gmax that different systems are capable of, what I'll call conventional systems are 4 or 5 Gauss per centimeter. We have a couple systems here that I'll call cutting edge systems that are about 8 Gauss per centimeter. And then there's a so-called connectome gradient, it's part of the big brain imaging consortium at several institutes. And they have specialized hardware that's capable of 30 Gauss per centimeter. But this is sort of the edges of engineering design right now. So this isn't going to change a lot very quickly because this is a well worked over problem. We saw the example on the bottom already. If this is the gradient, then that's the effect of on the field. And we can have lower gradients and have smaller effects on the field. In some ways, more interesting is what happens as the so-called peripheral nerve stimulation. So FDA puts a limit on what we call dB dt. The rate of change of the B field is a function of time. And if that's switching more quickly than about 20 Tesla per second, seconds are pretty long, Tesla is giant. If it's switching more quickly than that, you're likely to have so-called peripheral nerve stimulation. The models are more complicated than that, but that's a good threshold criteria. So let's look at the hardware that we might have. This is a high-end system that we have here, so it's kind of the maximum gradient performance that's commercially available. 80 millitesla per meter with a slew rate max at 200 Tesla per meter per second. We can talk about the time to rise. How long does it take to get up to your maximum gradient strength? That's just your Gmax divided by your slew rate. So we can hit maximum gradient strength in these systems in about 400 microseconds. So that's pretty quick. And if we're thinking about dB, this is our dt, right? This is how quick we can switch the field. What's our dB? Well, our dB is our gradient strength multiplied by some position that we care about. Our gradient fields are sensitive over sort of, call it 50 centimeters, half a meter at most, something like that. So we now have a distance and a rise time. We can calculate the field strength, and then consequently, what is the actual dB dt? So Gmax times the FOV max gives us that field over the rise time. So we can actually achieve in this system as much as 50 Tesla per second. So if we just run it, without any of the safety watchdogs running, we can easily stimulate and get peripheral nerve stimulation in any of you. So the systems have to monitor what the gradients are doing, make not quite these calculations, I'll show you in a second, but figure out what is the Tesla per second likely with the gradient waveforms you've chosen for your sequence or whatever. Is that going to cause a problem? So that's the simple version behind it. More complicated than that is the concept is that the switching magnetic fields actually induce electromagnetic field along the axis of nerves and physically cause them to depolarize. And if those are sensory nerves, then you're going to feel that, right? And there's no reports of people thinking things, but at least they're feeling things. When we talk about sort of the nerve response, we can have what we call a nerve response function. So the stimulus strength you have and the stimulus duration you have will tell you whether or not a nerve will fire, right? And so if the stimulus strength is high and the stimulus duration is short, you can cross that threshold. At the other end of the scale, if your stimulus duration is really, really long, but you're below the so-called real base, you can never depolarize that particular nerve. So we have to know something about the possible stimulus strength and stimulus duration, which is characterized by what's called the Rio base and the chronaxy, as to whether or not a particular system can lead to peripheral nerve stimulation. You don't have to get too, this is getting pretty detail oriented, but the idea here is there is a nerve response function that can be calibrated and is reasonably well known. And the MR system behind the scenes will actually use this function here to predict whether or not nerves will be depolarized. What does it look like? Well, it's 1 over the slew rate, and then it's the convolution of should be a convolution with the nerve response function that was on the previous slide. I'll show you just quickly some examples here. So let's assume that these are gradient waveforms that we care about, right? So on the top here, this is a gradient that's turned on positive and then goes negative. The green gradient here is just a triangular gradient that goes up, and this readout gradient goes down and is positive. These are actually real gradients that you would use for like a gradient echo sequence. What peripheral nerve stimulation depends on is the slew rate. So we have to take the time derivative of these gradient waveforms to get slew rate functions. If you take those slew rate functions and convolve them with the nerve response function and add them up, you can actually determine whether or not you'll cross that threshold criteria for potentially stimulating a nerve. And so this function, these particular gradient waveforms, when you calculate the slew rates and convolve with the nerve response function, you can see that partway into the sequence you'll pass threshold. And so there'll be a brief period of time where someone will feel this buzzing or tingling sensation. And the scanner actually won't let you run that. It'll say, no, you're going to go past the nerve response function or the threshold function. And so you have to change your sequence such that you can get below this threshold criteria and have an acceptable sequence. So this is being done sort of continuously on the scanner. So a lot of details there about peripheral nerve stimulation. The big thing is slew rate is what dictates how much or what likelihood you have for peripheral nerve stimulation. Last thing I think we'll talk about is this. I don't know if it's going to turn on. There was audio to go with this, but if you're in the MR scanner room, the one thing everyone always remembers, or one of the things people always remember, is how noisy it is. And it's the switching of the gradients. We turn the gradients on, we turn the gradients off. And we do that in the audio frequency range, meaning we're switching things on and off in the sort of hundreds of hertz to thousands of hertz frequency range. That's the sort of temporal frequencies of the gradient waveforms themselves. Those lead to mechanical vibrations that no one as of yet has figured out how to dampen. And so the systems end up being really noisy systems. We can compare it to sort of other possibilities here, but MRI gradients sort of full load or sort of going to your favorite concert or whatever, right? And they're not quite as bad if it's just sort of in conventional mode. And so that's why any subject that's going to undergo an MR exam is going to need earplugs or headphones that'll help with two-way communication as well. It's really a fascinating sort of engineering problem in that it seems like one that should be solvable, right? We know exactly the waveforms going into the system. You can predict the noise coming out of the system, and yet we haven't solved the problem of damping the noise enough to make it really comfortable for patients. So with that, two main things to remember about gradients and safety is that the so-called peripheral nerve stimulation and the fact that it works. Okay, so that wraps up for today. I said we might finish early. It's maybe 5 minutes early. Anyway, if you have questions, we can talk about the homework now for a little bit. If you don't have questions about the homework, if you already handed it in, feel free just to head out. If you do want to just have questions now, that's great. I prefer to sort of have it as a discussion just because sometimes the questions are the same for different people. If there are no questions.